actually did a PhD in mechanical experiments, and I have learned a lot about the different results. So, thank you.
Thank you. I was not expecting this crowd. So thanks for your time and your interest to attend my talk. I also would take some time to thank the organizers and Michaela to have me here and give some interest to listen to my work from my PhD. So today I'm going to show you the recent results from KATRIN experiment on neutrino mass, how we find as upper limit. And also I'm going to show you how we look for EV scale sterile neutrinos, what is the analysis strategy, and also give you some details about KATRIN experiment itself. So before moving further, I would like to start with understanding the importance of neutrino mass in the field of particle physics, because it would help us understand the theories that are beyond the standard model. So there are many theories beyond the standard model, and we do not know which one is true. So absolute neutrino masses or neutrino masses itself will help us understand few questions in particle physics that are yet not answered, like what is the nature of a neutrino? Is it Dirac or Majorana? Why are neutrino masses, as you can see in this picture, as compared to the other known leptons, why it is so small as compared to the other electron muon and tau? And what is the reason behind the matter-antimatter asymmetry? Similarly, in field of cosmology and astrophysics, neutrino masses do play an important role because the visible structure that we know so far is due to the fluctuations in the early universe. Due to the high abundance of relic neutrinos in the atmosphere, relic neutrinos, which are the so-called cosmogenic neutrinos, they carry very low masses, and at low mass scale, they tend to smear away a lot of uh, information from the early universe. So if you see a low, this is an old simulation from early 1996. So massive neutrinos can carry away, can smear out a lot of information from the structure formation. So we need to, so in cosmology and astrophysics also, it is important to know the neutrino masses. So now that we understand that why neutrino masses is important, let's now try to understand that what are the major approaches to look for neutrino mass. I have listed the major ones, that is coming from cosmology first, where the observable is the sum of neutrino mass eigenstates. So you can measure this observable by determining its effect, by measuring its effect of fluctuations in the cosmic microwave background, by looking at its impact of those fluctuations on the cosmic microwave background by satellites. So for example, like Planck satellites gives us the latest bounds coming from cosmology. Further, neutrinos are, they do not carry any electric or color charge. So they can be Majorana in nature. That means that they can be their own antiparticles. So that is the case for neutrinoless double beta decay searches, which is dependent on nature of neutrinos. And the observable is M beta beta, which is a coherent sum of neutrino masses, where the weight is coming from the electron masses itself. The leading experiments for these kind of searches, the limits are coming from GEDA, Carmen, and Cuore. But the limiting factor to these searches is reliable on the uncertainties in the nuclear matrix element of these double beta decay searches. The final one is the beta decay, which is completely reliable on the kinematics of the energy and momentum conservation. In that case, the observable is the square neutrino mass, or the square M beta particle, where it is the incoherent sum of neutrino mass eigenstates. Well, current terrestrial experiments cannot resolve between the teeny mass splittings of this mass eigenstate. So currently, what we are looking for, the observable is incoherent sum, and not looking for absolute mass scales itself. So the best limit for now coming from the beta decay searches is given by the KATRIN experiment itself. Now I'm going to focus, I have highlighted this beta decay thing because I'm going to focus all my talk afterwards on beta decay approach only. So before going further, I'd like to show that how the beta decay signal, how the beta decay spectrum looks like, and the differential spectrum of the beta decay is a function of neutrino mass that is highlighted in red that you can see. So if you look at the beta decay spectrum, where in x-axis you see the electron energy, in y-axis you see the relative decay amplitude, and you zoom into close to the endpoint of the spectrum. Is it okay? I just stay here. If you zoom into the endpoint of the spectrum, you can see that if there is a massive neutrino as compared to the blue one where there is no mass, then it can create a spectral distortion close to the endpoint region. The only caveat is what you can see already here, that the relative decay amplitude is low when it goes to the endpoint. That means the challenge is that we have very low, very less decays in this endpoint region. So to obtain enough, so what we need to precisely measure the beta decay spectrum close to the endpoint, we need enough statistics, and number of decays should be more. And for that, we need a stable source and a suitable isotope. I have listed several isotopes here, and among that, tritium proves to be an ideal candidate for beta decay searches, because here you can see the decay process of tritium, which decays to helium associated with an electron neutrino, followed by an emission of electron antineutrino. The major reasons that why tritium is a suitable candidate, it is because of the endpoint energy, which you can achieve in the experimental setup for the high voltage setup easily, and it has a half-life of 12.3 years. The major advantage of tritium is also that when tritium decays to helium daughter nuclei, there is only one possible nuclear transition state. So you do not need to worry about initial state or final state for the tritium transitions. And hence, beta decay approach that proves itself to be a most model independent approach, because compared to cosmology, it did not rely on any model assumption or any assumption on the nature of neutrino, whether it should be Dirac or Majorana. Now let's talk about KATRIN experiment. KATRIN experiment stands for Karlsruhe Tritium Neutrino experiment. It is an experiment present in Germany and in a beautiful city called Karlsruhe itself. And it also uses the best infrastructure available in Karlsruhe, that is the tritium laboratory. So KATRIN has the unique power to measure the beta decay spectrum precisely, just because it has two major requisites, that is the ultra luminous pure molecular gaseous tritium source, and it provides a decay. So basically, in the source you can find around 10 to the power 11 decays per second. So, and the stability is super stable, and the number of molecules that are present inside the source we know. So that is basically the column density, which defines the number of molecules, number of gas molecules in the source, which we know at a precision of 0.1%. And also the other thing that KATRIN has, that makes KATRIN more powerful is the spectrometer, which is given by the magnetic adiabatic electrostatic filter, which is basically providing excellent energy resolution with very low background. And these are two essential requisites for measuring the neutrino mass precisely. So let's now discuss about the experimental setup. The entire setup spans up to 70 meters in length. You can divide the entire setup into two parts. The first half is a source and transport section. Here is the windowless gaseous tritium source, and followed by the differential pumping section and cryogenic pumping section to reduce the flow of tritium by 14 orders of magnitude when the tritium is injected here. So what we do is we inject tritium in middle of this windowless gaseous tritium source and pump out continuously from these two ends. Followed by the second part, which is the rest 35 meters of the entire span. Here it is the spectrometer and the detector section. So what is happening is beta electrons are isotropically emitted in the source, and they are moving in parallel direction with respect to the magnetic field. This magnetic field is coming from the superconducting solenoids that are present in the beam line, and this electron beam is transformed into a parallel. So this is following in parallel to the magnetic field lines, and these parallel lines are moving against the retarding potential set by the cylindrical electrodes inside the main spectrometer. So only those electrons with enough energy to surpass this retarding potential will be reaccelerated and be collimated onto the detector. Here, the detector is a semiconductor type detector. It is highly segmented. So by varying the retarding potential in steps, one can measure the integral spectrum. So basically we just measure in an integral way. So you vary the retarding potential and you measure the integral way. And here you can it is a demonstration of how the integral rate versus the retarding energy looks like. I will not go into details of what are these lines. It is just for demonstration, because in my next slides, I will show that what are these different branches for active neutrino and sterile neutrino and so. All right, so this is all about the KATRIN setup. Now, if there is experiment, there is also sources of systematics, which you also need to take into account so that we do not give any biased analysis or we do not perform any biased analysis or any, we want to avoid as much as possible the impact of systematics on the physics observables that we estimate. So over the course of KATRIN, we have realized a lot of different systematic parameters related to source part, related to magnetic field part, and also there are different background components. So I'll not go into details of every systematic parameter, but the reason to mention this is that KATRIN spends substantial amounts of its time to estimate to estimate and to measure also the systematics. So there are individual groups in our collaboration who are continuously monitoring and measuring the systematics and calculating their impact on the physics observables. So yes. No, so what we do is we just, for the cylindrical electrodes, we just change the retarding potential. Let's say the endpoint of energy is coming, we know the beta decay spectrum's endpoint energy. So a neutrino, our major goal is searching for neutrino mass, and neutrino mass impact will be very subtle, close to the endpoint energy. So we just vary in many steps, we just vary the retarding potential. And so we just tune the cylindrical electrodes and vary the retarding potential. Yes, so only those electrons. So electrons are coming with all ranges of energies. So what we are selecting is only because it's like this. So when we apply electric retarding potential, it creates the retarding energy, and electrons are moving against this retarding energy. So only those electrons which have the enough energy to surpass this filter. This now acts as a filter, like an electrostatic filter. Yeah, could be. Depends on the solid angle also, because the starting energies, it depends on a lot of factor. Our acceptance angle is up to 51 degrees. So depending on this is the solid angle, depending on depending on the starting energies and up to how much, because we also have so at source we have some magnetic field strength of 2.1 Tesla, and there is a pinch magnetic field, pinch magnet, which is the maximum magnetic field that is present in the entire beamline. It is around 4.2 Tesla. So that defines our acceptance angle. So if electrons are coming with a large angle, it will not go because it will be just reflected back. You are right, it is challenging our statistics, but still we have 10 to the power 11 decays per second due to our ultra stable source. So nice question, thank you. Okay, shall I proceed? Okay. Now, I will like to take some time to show you the theoretical prediction of KATRIN model. So what we have, as I have already shown you, this is a differential spectrum, which is a function of kinetic energy of electrons and neutrino mass. And that is directly convolved with the experimental response of our experimental apparatus. And then that gives us the integral spectrum here. So this is how our model looks like. This is the equation. And I have highlighted some parameters, which you'll see in my next slide. So just to give you an idea that how much, how we are measuring, so you can see that here we have the retarding energy. So these are our measurement points. And you can clearly see that close to the endpoint, we spend maximum amount of our time where the neutrino mass impact would be very subtle. And this is the spectrum, this is the rate plot where you can see the integral spectrum. Here is the beta decay spectrum, and we are also including few background points. If you want to know more details about how the model is written, what are the exact things going into the model, because there are multiple things also coming from the systematics that are fed into the model, you can find all the details here in these papers. Okay, now one slide on how we do the neutrino mass analysis. So you have seen the model. Now let's see, because for the analysis, you also need data and then compare the model to the data. So we take measurements in form of campaigns. We call them KNM, KATRIN Neutrino Mass Measurement Campaign. And in each campaign, there are scans. There are basically runs or scans, which are in order of few hundreds. And each scan can take up to 3 hours. And within a scan, there are around 30 high voltage set points, 30 retarding potential, or let's say 30 retarding energy points. So And in the analysis range, we go 40 eV below the endpoint to 135 eV above the endpoint so that we can also include the background points. Now, as I have also shown you before, the equation for model, what we do is the model is a function of retiring energy and theta, which is the nuisance parameters. It is fitted, so the model is fitted to the major spectrum, and what we obtain are some of the model from the parameters that I have listed. What we obtain from the fit. By fitting, I mean that we are using chi-square minimization. So chi-square is nothing but negative log likelihood. Either you minimize chi-square or maximize the log likelihood. So when we do the fit, we obtain some model parameters, and I have listed here a few model parameters, that is signal amplitude, effective endpoint energy, and neutrino mass, which is our parameter of interest for neutrino mass analysis. To perform a very robust analysis, we have a blinding protocol. For that, we first apply all of the statistical methods that we have chosen for analysis on MC data, on Monte Carlo data. So Monte Carlo data is basically the simulated data, which is obtained from the exact experimental configuration that is used for the real data. First, we have performed analysis on that. And the next step for the blinding protocol is we hide the final state distribution of the tritium molecules in the source. So we just apply some width of the final distribution before applying that to the real data, before seeing the real neutrino mass. And to check also the robustness of the analysis, we have two software teams. One team performs analysis on a C++ based framework, which does a precise calculation of the response, of the experimental response. And the other team, basically, it uses neural network approach so that it can make a fast calculation of the model. And then we compare our results with each other at every step of our analysis before doing it on data first. So here I'm going to show you the latest results of neutrino mass. So what you can see here, I will go through the plot quickly. So this is the likelihood profile on the neutrino mass, on the square neutrino mass. The solid, the green line is for first campaign, the result from first campaign. The blue line is the result from the second campaign, and the gray one is our latest result based on the first 5 campaigns. The dashed line is basically the statistics when the statistics are included only. For this is the likelihood profile for the statistics only case, and the solid line is the case for statistics and systematics included. So that is our main result. On the top panel here, the gray line is basically for KNM 1 to 5. This is the central value on neutrino mass shown by the dot here in the top panel, given by the 68.3% confidence interval around the central value. So these vertical lines correspond to the statistical limits for those set of data. So the best fit that we found is around is at minus 0.14 is negative, and the combined result from so the best upper limit that KATRIN at the moment gives is the less than 0.45 at 90% confidence level. So now I wanted to discuss about other physics goals of KATRIN experiment. So the primary goal is to, of course, measure the neutrino mass, but there are also a list of physics topics that KATRIN looks for, because close to the endpoint region, the statistics is so high that we can use the same data set to look for other physics topics like general Newton interaction or the non-standard interaction, search for light extra bosons, local overdensity of relic neutrinos, Lorentz invariance violation, and EV scale sterile neutrinos. If you are interested in knowing the status and the results from the other physics topics, you can find the relevant and respective papers listed here. But I'm going to focus mostly on EV scale sterile neutrinos. And here I'm going to take a pause and start by explaining why we are interested in looking for EV scale sterile neutrinos. So let's start by looking at the early picture of the fermionic sector of standard model, where all the fermions come with both left-handed and right-handed counterparts, except for the neutrinos. Neutrinos are that's why considered to be only half of the particle and were massless unless neutrino oscillation was discovered. And thanks to Professor Arthur McDonald and Takaaki Kazuta, due to their excellent discovery, we got to know that neutrinos flavor could mix with each other and they have masses. So if you look at the oscillation probability of a flavor over a distance over energy, you can see that how it is changing. And this oscillatory behavior can be expressed by this equation, where neutrino mass eigenstates can be expressed as a linear combination of flavor eigenstates. So now that we know that neutrinos have mass, we also need to understand that what is the reason behind neutrinos having mass. So that can be done by extending the standard model so that we can understand what is a generation mechanism of neutrino masses. And the simplest way to do that is to add more neutrinos into the picture. But these neutrinos do not experience any weak or electromagnetic interactions, and these are sterile neutrinos. They are neutral hypothetical particles, or let's say standard model gauge singlets. And currently, it is very difficult for any terrestrial experiment to detect them because they are not experiencing any known fundamental forces like weak or electromagnetic interaction. So the only way to detect them is via looking for their mass effects or by looking at their mixing with other neutrino flavors. Currently, there is no theoretical limit also on their mass scales or on the number of these new neutrino species. So they can exist at any possible mass scale, starting from EVs to TeVs to GeVs and so on. So my work that I'm going to show you today is focused on EV scale sterile neutrinos. And before that, I would like to show that how we introduce an EV scale sterile neutrinos to the 3 neutrino mixing scheme. The simplest way to do that is to add one heavy sterile neutrino to the existing 3 neutrino mixing scheme. In that way, building upon the 3 cross 3 PMNS matrix, you can extend it by a 4 cross 4 matrix. And this scheme is allowed by long baseline experiments, solar experiments, atmospheric, and also it acts as a perturbation to the 3 neutrino mixing scheme. So once you add this, you can extend this PMNS matrix and you get a mass ordering in the following way with additional mixing parameters. But the sterile mixing to the other active neutrino state should be really small if you want this scheme to be existing and to be also allowed by other experiments. Experimentally also, there were motivation for sterile neutrinos. There were some anomalies that were observed in appearance. So sterile neutrino can be observed in neutrino oscillation searches through their so basically there are certain anomalies in appearance-based channels where in experiments like LSND and Miniboon, they found excess of electron neutrino events, and in experiments like the gauge, Thalex, and Galax and Sage, there were some observations where they found a deficit of electron neutrino events. And they led to anomalies. They're called anomalies. So recently, not recently, but it was in 2022 that BEST also reaffirmed Galax observation, and it was called the gallium anomaly. So, but when we look at the global, global analysis based on this appearance and disappearance searches, they are at very severe tension. So they are around 3 to 4 sigma tension. So neutrino oscillation is not the only way to search for sterile neutrinos. Rather, we can also use model-independent ways like beta decay to look for and to determine sterile neutrinos. So let's see how the signature in the beta decay of a sterile neutrino looks like. So in a beta decay, as we know that an electron neutrino flavor is emitted along with the electron neutrino. So if the electron neutrino flavor contains an admixture of a new neutrino mass eigenstate, which is sterile, and it has a mass higher than the active neutrino masses, then it will lead to an additional spectrum in the branch whose endpoint would be shifted by the mass of the sterile neutrino, and amplitude would be corresponding to the mixing. Amplitude of this new branch will be corresponding to the mixing. So if you look at the differential decay rate equation now, it is a function of not only the kinetic energy and electron and the square neutrino mass, but also a function of sterile neutrino mass and mixing. And it is a sum of 2 independent branches. The active branch is characterized only by the active neutrino, and the sterile neutrino characterized by sterile mass. So if you take a combination of these 2 branches, which is given by this dashed green line for the active case and the blue line for the sterile case, if you combine these 2 spectrum, it will be, then the sterile neutrino spectrum will be seen, sterile neutrino combined with the active neutrino spectrum will be seen like this red line, where the sterile neutrino will manifest itself as a kink in the spectrum. So the position of the kink corresponds to the sterile mass, and the amplitude of the kink is proportional to the mixing. Okay. Now, since I have already shown you how the model in the KATRIN experiment looks like, Now I am going to show you how the model changes when we add sterile neutrino parameters. It's nothing where it's just that in the differential equation where basically our integral spectrum is a convolution of the response and the differential equation. We just add two more additional parameters to our model. This is the sterile neutrino mass and mixing. So here is a simulation of a sterile neutrino signal. So in the lower plot, you can see the measurement time distribution. And in the upper plot, you see basically the blue line is for a simulated best fit model for a 3+1 neutrino model, and the dots are the KATRIN data points. And if you take the ratio between the active neutrino branch and sterile neutrino simulated at a mass at a signal of a mass of 100 and mixing of 0.05, you can see that all the other observables for both the branches stay the same. You just add one more sterile neutrino at this mass. How will the sterile neutrino look like is shown in this plot. This is the ratio, or we know the so-called residual, which is the difference between the data and model. The sterile neutrino will show up itself as a bump in the spectrum. So this bump, so this lower peak is corresponding to the mass, basically. Okay. Now I would like to show you the status of data collection for for KATRIN experiment. So so KATRIN has, in October 2025, KATRIN has already finished its planned 1,000 days of data taking. And so from the first two campaigns, KATRIN has already published its results, which were published in Nature Physics with an upper bound on neutrino up to 0.8 eV at 90% confidence level. And that corresponds to 6 millions of electrons from our entire data set. The results on neutrino mass that I have shown today and the results on sterile neutrinos that I'm going to show is based basically on 36 millions of electrons, which corresponds to a quarter of KATRIN's total collected statistics. So over several runs and several campaigns, KATRIN has also made several changes to the experimental setup and also to the column density so that we can obtain an optimal case of operational settings for the entire experiment. Okay, now moving forward, since I have already mentioned that there were already a publication on sterile and on neutrino mass for the first two data sets, I would like to show the difference, what happened from the first two data sets to the first 5 data sets, what are the major changes. So for each, I have already mentioned that our measurement points are retarding potential. So for each retarding potential, this is our detector. For each retarding potential, the data were effectively combined from all those pixels highlighted in green here and were effectively considered as one data point. So effectively, for KNM1, for the first campaign, there were 27 data points, and for KNM2, there were 28 data points. But okay, and also the results, we did not find any significant sterile neutrino signal, and we published our results in PRD 2022. But from third campaign onwards, there was a major change in the experimental configuration. In order to reduce the background of the main spectrometer, the flux volume of the spectrometer was also reduced. And what this creates, so this of course this helped in reducing the background by a factor of 2 for the main spectrometer, but this also affected us otherwise. It created, so there was an inhomogeneity in the magnetic and in the electromagnetic field. So if you map the magnetic field onto the detector and the electric field, there is an inhomogeneous distribution. And if this inhomogeneity of the pixels is not taken into account correctly, then that could lead into a severe bias in our analysis. The major details of this experimental configuration changes are also published in this, which you can find here. So just to take this inhomogeneity of electromagnetic field into account, what we did is for all those pixels with same response, we grouped them effectively into one patch. So there were total number of 14 patches, and each patch consisted of around 9 pixels. So finally, the total number of data points was increased by a factor of 14. And here is a demonstration of how the patch-wise, how the spectrum looks like, and grouping them together and analyzing them is more challenging. So here I have listed some of the complexity in our analysis. So we have around 1,609 data points across the 5 campaigns. And we also take into account the correlations of systematic parameters. And these correlations can be across data sets. These can be also across patches within campaigns. And there are around, so if you make a sum of these correlations, correlated systematic parameters, they are around 144. So when we take all of these into account, it makes the computational calculation of our model very expensive. So here I am focusing now on how do we do the sterile neutrino search, because I have already explained for neutrino mass. So for sterile neutrinos, we do we basically we perform fit, which is basically again we obtain the chi-square, which is basically um, finding the negative log likelihood of with respect to the nuisance parameters. We fit the model to the data and we minimize the chi-square, and this is done on the method of grid scan. It is based on the frequentist approach, not on the Bayesian approach, just to mention. And what we do is at each, so the grid point is defined for up to from these values for the mixing to a mass of 1600 ev square, that is 40 ev below the endpoint, which corresponds to 1600 ev square up to the mass that we go. And at each point on the grid, we perform a fit. So that fit means we minimize the chi-square for that particular value of sterile mass and mixing. We also perform a chi-square minimization for the null hypothesis. And in our case, the null hypothesis is with zero mass and zero mixing. In our primary analysis, we assume that the active neutrino masses is very small as compared to the sterile neutrino mass. So we consider the active neutrino mass to zero. We fix it to zero. And our test statistic, that is the delta chi-square, is basically the difference between the chi-square null and the chi-square global minima, which is the best fit. So if you look at this plot, which is the simulated plot, if there is no sterile neutrino signal, then we will obtain this open contour given by this left side of the plot and the best fit marked as the cross here. And if there would be a significant sterile neutrino signal, then it would be given by a closed contour. And these are all simulations. The significance that we have chosen for our contour reporting is at 95%. And this comes from, this has done at delta chi-square of 5.99, which comes from Wilks theorem. And I will talk about Wilks theorem also shortly. Yeah. Yes. No. So in our simulation, there is no sterile neutrino signal. And in this simulation, we introduce the sterile neutrino signal. Here, because what we do is our chi-square, as I said, is chi-square null. So this is always the best fit. The chi-square, this is the chi-square minimum from all of these 15 points, for all of these 1500 points. But here there is no injection. It should be close to zero, but there is also fluctuations. There is statistical fluctuation. Yes, it could be somewhere else. Okay, so now to test the robustness of our entire analysis and statistical methods that we are using, we also do the similar kind of blinding procedure. We first perform our test our procedure on Asimov data, which is basically the same, basically the data obtained from the same experimental configuration as of the real data, but without statistical fluctuation. There in our simulation, we use these values of neutrino mass and sterile neutrino mass and mixing. And what you can see here are the sensitivity contours for the mass in y-axis and mixing in x-axis. This is a very busy plot, but I will just highlight the pink line, which is the combination of 1 to 5 campaign. This is a sensitivity contour. So what does the sensitivity contour mean? It means that it just shows the distinction power of KATRIN at 95% confidence level with respect to the null hypothesis. So if there would be a significant sterile neutrino signal at specific mass and mixing lying right to the contour, then KATRIN will detect it at 95% confidence level. But if it lies to the left, then KATRIN will not be able to detect it because it is beyond KATRIN sensitivity. Similarly, we also estimated the impact of systematic uncertainties into our analysis, and for different sterile masses ranging from low value to high value, you can see that our analysis is dominated by statistical uncertainty. Further, there are also other systematics that are also dominant after the statistical uncertainty that is coming from the column density times the inelastic cross section that is basically determining the amount of gas molecules in the source. But what we can say, the final message from this plot is that our uncertainties are statistically dominated. Okay, now here I'm going to show you the exclusion limits from the first 5 science runs. KATRIN has already published his results based on the, so these are the initial results from the first 2 campaigns given by the orange line. This is the exclusion bound now. So KATRIN found no signal. And then this is the blue line is the latest limits from the first 5 campaigns. KATRIN also found no significant sterile neutrino signal. So if you want to look at the individual significance of each campaign, here are the values, and nothing is crossing over 95% confidence level. So we do not find. The significance that we have chosen is based on the assumption coming from the Wilks theorem, which says that our test statistic, that is the delta chi-square, follows a chi-square distribution with 2 degrees of freedom. But since most of the conditions of the Wilks theorem were not met, so I performed a Monte Carlo study where there were 10,000, where I chose 10,000 spectra with statistical fluctuations, estimated the delta chi-square and looked at the chi-square distribution. Here is the probability density function that you're looking on the left, and on the right you're looking at the CDF. What we found from the Monte Carlo study is that the delta chi-square critical value obtained from the empirical chi-square distribution is close to the delta chi-square critical value from the Wilks. So from this, we also confirmed that the significance that we are choosing, even if some of the conditions were Wilks theorem are not met, still our significance holds at 95% confidence level. And the Wilks theorem is thus applicable in our analysis. Okay, now let's look at the results from other complementary experiments, neutrino oscillation experiments based on disappearance searches. I don't know if it is visible to the end there. Sorry if the font is small. But these are the exclusion bounds. So I have listed it. If you can look through my slides later, you can see that I have listed the exclusion bounds with the confidence level, and the one like BEST and gallium, for example, they are allowed regions. They are not excluded regions. That's why there is no confidence level mentioned here. So these are the latest limits coming from the disappearance searches. And KATRIN physics parameters, that is the sterile neutrino mass square and the mixing, they can be also compared to those oscillation based experiments by using the following translation of parameters expressed by these equations here. And this is the KATRIN results from the first 2 campaigns. Here is the sensitivity contour from the first 5 campaigns, and here is the final exclusion band that is also now published last year in Nature. And what you can see that KATRIN covers most of the region of the allowed region from BEST and gallium, and it is also, so neutrino 4 is an experiment which almost claims the discovery of a sterile neutrino at certain confidence, and KATRIN rejects their hypothesis based on the assumption that if the active neutrino mass is smaller as compared to the sterile neutrino mass. Okay, now what we have also seen, we have observed that this so we have performed a sensitivity forecast based on the 1,000 days of data. We have seen that this is given by the blue dashed line here. For low masses and for low masses, we see that our current exclusion based on first 5 campaigns is better than our final sensitivity based on 1,000 days. And we wanted to understand why that is the case. And we performed again a band test with fluctuated spectra more. And what we found from these bands that this could be due to statistical fluctuations. And it is explained by statistical fluctuations by looking at this 1 sigma and 2 sigma band. They are under, these lines are falling under this band. Okay, now talking about the summary. I have already shown you the latest results on neutrino mass and sterile neutrino, and KATRIN is giving the most stringent bounds, and it is giving the world's best limit based on the beta-decay searches on the neutrino mass. Similarly, it's also giving the best exclusion bounds for sterile neutrinos coming from the beta-decay probes. And KATRIN is also uniquely testing the short baseline anomalies through the beta-decay searches. Currently, we have found no sterile neutrino signal. Oh, sorry, my no is missing here. It's my bad. Yeah. And the exclusion limits are complementary. Please, I'll not upload this. Yeah. And this is and the exclusion limits are complementary to other disappearance searches. You can find our latest releases in these two papers in Nature and Science. And as an outlook, since we have already finished 1,000 days of planned data taking, analysis is ongoing on the rest of the 230 millions of events. So please be tuned for our new limits and new results. And KATRIN is also at a stage where it has planned its detector upgrade, that is the Tristan detector upgrade, where it will scan the full beta decay spectrum to search for KEV scale sterile neutrino signal and also do searches for more physics beyond the standard model. Yeah, thank you. Oh, I just wanted to add the no there because you're recording it. So. Yes, sure.
Maybe you mentioned that what is the class
What, can you please repeat?
the maximum that
The mass limit, because I don't understand. I want to make sure that if I am understanding your question, we are trying to find the mass, and we allow neutrino mass to be free in our FITs, in our search space. And if so, the analysis range that we are choosing for our analysis. So for first two campaigns also, it was up to 40 eV below the endpoint, and for the first 5 campaigns also, it was 40 eV below the endpoint. So we do not change our analysis range. Yeah. Yeah. Ah, okay. Yes. So currently our target sensitivity, or based on the understanding of all the systematics that we have, our target sensitivity is up to 0.3 EV at 90% confidence level. So 0.3. 0.3. So, but based on within the analysis window of 40 EV below the endpoint, we also need to understand we can go to 60 EV below the endpoint, so we have more statistics, we can improve our bounds, but we need to also understand for that range our systematics better. And I've also mentioned this in my talk that KATRIN is spending substantial amount of time in spending and analyzing the systematics and impact of systematics. So for us now, it is a challenge that we cannot analyze up to 60 or 90. We have the data on our disk, but that is just that up to 40 EV, we understand our systematics better. That's why these limits are all up to 40 EV below the endpoint. And these are the, this is basically the likelihood profile for the neutrino mass.
Can I ask a question from online? Hi, Shelley. Sorry I missed your talk. I listened to most of it from the car from the airport.
Yeah.
What is it that's limiting the sensitivity? Sorry.
Microboon. Yeah, the thing is, microboon is an appearance channel based experiment. So where the observables is no, we are looking for UE4, the sine square theta thing parameter. Microboon also looks for UE4 and mu4. So it is appearance-based channel. So our sterile neutrino bounds are can be only compared to disappearance channels, where they're sensitive to mass square difference between active and sterile, and mixing between electron and sterile.
Art has a question online.
Oh.
Art, go ahead. I need to speak. Art. You can ask your question now.
Okay, thanks. Sorry I missed your talk, Shelley. I'm coming from the airport. The Tristan experiment, what changes will be made to improve the sensitivity for sterile neutrinos going forward?
So for the Tristan experiment, what changes will be made going forward for the sterile neutrino?
Yes. So currently with our semiconductor type detector, we are measuring in an integral mode. And for Tristan detector, since we need to scan the full spectrum, full differential spectrum from the beta decay, it will be operated in a differential mode. So for that, for the integral spectrum, since we are looking, our focus is mostly on neutrino mass, we just go for few eV below the endpoint. But for the Tristan, for KEV search, we have a full bed differential spectrum with a differential measurement. And in that case, our detector is also operated to a silicon type detector. So I hope that answers.
So what's the change in your detectors that enables you to do that in a differential way?
Okay, so yeah, in that case, so we are increasing the detector pixel size and the charge readouts of these silicon type detectors.
Okay. Thank you.
Thank you.
Can I ask another question then?